If you read the article about dating the Earth, you probably were a little bit confused with the description of how Boltwood and Rutherford were able to make the first quantitative measurements of the age of rocks based on radioactive decay. So I thought this would be a good opportunity to explain exactly what they did, and in the process explain some of the basic principles behind radioactive decay. So first of all, let's just talk about the schematic here. We have uranium, radioactive uranium, decaying to form radioactive radium, which in turn decays to form lead. Now back when Boltwood was doing this, they didn't know about isotopes yet. So all they knew was that uranium was radioactive and would spontaneously decay to produce radium, and then radium similarly was radioactive and would spontaneously decompose to produce lead. And they knew nothing about the different isotopes. So this is a very, very simple, simplistic view of sort of a bulk element. A bulk element changes along the decay from uranium to lead. Now, in fact, this is not exactly how it goes. It's actually known to be much more complicated than that. What actually happens is uranium actually first decays to thorium, and then thorium undergoes a whole bunch of different steps, intermediate steps to get to radium. And then radium initially decays to form radon, and then radon goes through a whole bunch of intermediate steps to eventually decay to lead. But the key point here is that these steps all don't happen at the same rate. The decay of uranium to thorium, this step here, is slow, very slow, because it's got a very long half-life. Similarly, the decay of radium to radon here, this one is slow too. In contrast, the transformations of thorium to radium, all of this part here and all of this part here are really fast. They have very short half-lives. So for example, if you think about the decay of uranium, it very slowly decays to thorium, and then almost instantly the thorium decays to radium. And as a result, we can think of this as uranium decaying directly to radium, even though in fact that's not exactly how it happens. But for all intents and purposes in geologic time, that's how it happens. And then once again, radium decaying essentially directly to lead, even though in fact it goes through intermediaries. But the bottleneck step here is the bottleneck steps here are the decay of uranium to thorium and the decay of radium to radon. So those are the intermediaries that persist like this in this generalized decay schematic. Now, the first thing we need to understand is that one of the observations that Boltwood made, or one of the inferences he made, was that given enough time, this system here is in equilibrium. And what we mean by that is that if we consider the reservoirs, we have a big reservoir of uranium, and then a reservoir of radioactive radium, and then a reservoir number of atoms of lead here, right? These things now, material is flowing between them. So uranium's decaying to radium and radium's decaying to lead. And at equilibrium, the key point is that these red arrows here are equal. In other words, the flow of radium coming in is equal to the flow of radium coming out, and as a result, the concentration of radium is constant. As much new radium is being formed by the decay of uranium as is decaying to form lead at equilibrium. So let's focus in on then that equilibrium for the intermediate decay product of radium. So let's focus in on this here. Now, this is a great chance now to actually think about the mathematics that describe the decay here. So the first part here, the input here, radium in, is governed by the decay of uranium to radium. Now all decay, so this is the parent here, and that's the daughter. Now, all of these decays are governed by the same equation, and I'll write that like this, that the amount of the daughter is equal to the amount of the parent times 1 minus 1/2 raised to the power of t over h, where I'm using h to mean the half-life. So it's a number of years. Now, notice what this says. This is the amount of daughter. It's going to depend on the amount of parent, and then it's going to depend on the age and the half-life. The second part here, okay, this second part here, this describes the decay. We can actually plot this up. If I were to graph this up, this is time like this, and this goes from 1 to 0. This graph sort of looks like this. That's what it looks like. And the shape of this graph, this part of the equation, depends on the half-life. If the half-life is really, really short, then the graph kind of looks like this. And if the half-life is really, really long, then the graph kind of looks like this. So that controls the rate at which the parent is decaying to the daughter. Now, what we're interested in is the instantaneous rate of change, the instantaneous rate of production of the daughter isotope. So we're interested in this slope right there, okay? And you can see that slope changes. For something with a really short half-life, it's really steep, and with something with a really long half-life, it's really shallow. So we want this slope here, which describes the instantaneous rate at which the daughter isotope is produced from decay of the parent. And that's actually a calculus problem. That's actually not that hard. What we really want to do is take dt, and so all we really need to do is take the derivative of this thing here. And it turns out that's not something that's too hard. You probably did it back in your calculus days. And what we can show is that the instantaneous rate then, this rate at t equals 0, that is equal to a constant times the concentration of the parent divided by the half-life. So that is the instantaneous rate of production of the daughter isotope from the parent isotope. Okay, now, so this is what the mathematics tells us. This is the rate, instantaneous rate. Now, going back to our little equilibrium model here then, what we said was that this input here has to equal the output here. So we can set up those. Let's actually take a look at what those two equate. Let's redraw that and then set that up here. So here's our reservoir of radium. And radium is coming in here and going out there. The rate in is governed by the decay of uranium to radium, okay? And we can write that now using our equation as the instantaneous rate, the accumulation of radium, is equal to this constant times the concentration of uranium, that's the parent, divided by the half-life of uranium. And let's give it a different color to make it clear, okay? So the rate out here, now make it red, that is the amount that's the amount of lead produced. But that is the same thing as the negative change in the amount of radium, because radium decays to produce lead. So these are, and absolute values are the same. And that will equal this constant times the concentration of radium. That's now the parent divided by the half-life of radium. So these guys, the absolute value of these guys have to be equal. Now the constants are the same, right? Constants are the same. So what we can say then is that the ratio of the concentration of uranium to the half-life of uranium has to equal the ratio of the concentration of radium to the half-life of radium. Now, we know that the half-life of uranium is huge. It's on the order of many billion years. And it's much, much, much larger than the half-life of radium, which is on the order of 2,000 or 3,000 years. And so since this number is so much larger than this number, right? Therefore, this number has to be similarly much larger than that number, right? If these two ratios are the same. And so as a result, we can conclude that the equilibrium concentration of uranium is by the same amount much, much, much larger than the equilibrium concentration of radium. In other words, when we went back to our picture here of this picture here showing our three reservoirs. In fact, it should look, if I were to try to draw them to scale, it would sort of look like this. We have a giant reservoir of uranium, and then a very small reservoir of radium, and an almost really tiny reservoir of lead. And what's kind of cool here is this shows exactly how radioactive decay works. The inputs of radium depend on the concentration of uranium, and they also depend on the half-life. Well, half-life of uranium. Well, in this case, we have a very long half-life, so a very slow decay rate, but an enormous reservoir of uranium. So as a result, the amount of radium trickling in is exactly equal to the amount of radium trickling out, which depends on a much smaller reservoir of parent, but a much faster half-life. So remember, in radioactive decay, the rate of accumulation, the rate of production of the daughter isotope depends both on the decay constant and on the amount of parent. So in this case, we can have, even though the decay constants are so different, so the half-lives are so different, we can still have equal amounts of radium coming in and out if we have vastly different reservoirs of uranium and radium. Now, here's the key now, okay? If the amount of radium then at equilibrium, if this amount here is constant, then the rate of accumulation of lead then, I can write this as, let's give it a different color here. I can write that the change in the concentration of lead with respect to time is equal to that constant times the concentration of radium divided by the half-life of radium. But here's the key now. If in this particular case now, the concentration of radium due to equilibrium is a constant, as is the constant. So we can write then, so in other words, because everything on the right-hand side of this equation is a constant, everything here is a constant. And we can write this then as the change in the concentration of lead with respect to time is equal to, it turns out to be 0.00027 times the concentration of radium. Now, in the article, they describe this number here. This is equivalently 270 parts per million. You could describe it as, you could also describe it as 270,000 parts per billion. They're the same number, just different ways of expressing the same thing. Now, since this is a constant here, we can actually integrate this. It's really easy and solve it and plot it. So let's actually do that. Let me move down a little bit here. This is super duper easy calculus. So what I can write here is that I'll rearrange this to say that dt is equal to 1 over 0.00027, which turns out to be 800 over the concentration of radium times dPb. And if we integrate this, we end up integrate this, remember integration, right? These are all constants there now. And we assume that there was no initial lead. We can integrate this real simply as T equals 3,800 times the ratio of the concentration of lead to radium. Piece of cake. If I know the lead-radium ratio, I can figure out the age since lead has been accumulating. So in other words, maybe it's easiest to plot this. I usually like to plot things. If we plot time on this axis and the lead-radium ratio on that axis, this should be a line. It's a line like this. So if you tell me the lead-radium ratio, then I will tell you the time, right? It's initially 0 because there is no lead, and then as radium decays, the lead as radium decays and produces lead, then this ratio increases. So at this point, you maybe wonder, well, why didn't Boltwood just use this? And the answer is that at the time, this was really hard to measure. Okay, it's kind of hard to measure radium. It's a lot easier to measure solids than gases. So what he did was he took advantage of the fact that it was known that the ratio of radium to uranium in all rocks, regardless of age, was nearly a constant equal to about 3.8 times 10 to the minus 7th. In other words, there's vastly more uranium than radon, which is what we said at equilibrium. So he said, okay, then I can just sort of use uranium as a proxy for radium because it's easy to measure. So I can say that the amount of radium is going to equal 3.8 times 10 to the minus 7th times the amount of uranium, and I'll just plug that value right in there. Right in there. Right in there. So, in other words, I could write that T is equal to 3,800 times the concentration of lead divided by the amount of concentration of radium, but then I'll substitute that. I'll equal 3,800 times the concentration of lead divided by 3.8 times 10 to the minus 7th times the concentration of uranium, because that is what the concentration of radium is equal to. And then it's just a matter, right? I can then say, okay, I just nearly need to carry out that division to get a single constant, and that can be shown to be essentially 1 times 10 to the 10th, or 10 billion, times the ratio of lead to uranium. So I'm just using uranium as a proxy for lead. And so, in other words, if I want to draw the same diagram here now, let me go back actually over here. So, same diagram here. This is time, right? And these are ratios, okay? We said that the graph of this is the lead radium ratio, right? So there's a direct relationship between time and the lead radium relationship. Well, I could also, because radium is proportional to the amount of uranium, I could similarly show with a much steeper slope. These slopes are not to scale here now. This here is the ratio of lead to uranium. So the same graph now, but now I'm actually measuring the ratio of lead to uranium, and those are things that are more easily measured. So the idea then is, once again, look at this equation. I'll rewrite it here, that the age is equal to 1 times 10 to the 10th times the ratio of lead to uranium. All of this done without knowledge of isotopes. Pretty amazing, right? So that's it. And it's so easy to use then. So for example, you go out, for example, let's use an example here. We go out, we measure a rock that has a lead uranium ratio of 0.02. Then we would infer that that rock has been accumulating lead since, in other words, its age over a period of 1 times 10 to the 10th times 0.02 years, and that turns out to be 200 million years. So that rock, we would say, is 200 million years old. A rock that was 400 million years old would have a lead uranium ratio of 0.04. In other words, it's accumulated more lead over that time. Now, you're probably wondering, why did he do it this way? Wouldn't it have been so much simpler just to consider the radioactive decay of uranium directly to lead, right? And then we could write, well, the concentration, you remember what that looked like, the change in lead with respect to time, the rate of production of lead is going to be equal to that constant times the concentration of uranium divided by the half-life of uranium. Now, in fact, the concentration of uranium changes, but since the half-life is so long, if the age of the rock is relatively short compared to the half-life, we can consider this more or less a constant. And then we have the same problem we had before. We just have everything on the right-hand side is a constant. And then we could integrate this, and we'd end up with an expression that says T is equal to the half-life of uranium over C times the ratio of lead to uranium. So this is analogous to what I did before. And so, in other words, if we forget about radium, just using the uranium directly to lead relationship, because after all, the decay of radium to lead happens relatively very, very quickly, right? We can directly get an equation that allows us to calculate directly the age of a rock just based on its lead to uranium ratio, once again making the small assumption that the concentration of uranium doesn't change very much. And essentially, this is what he did before. The reason, though, he couldn't do this compared to the way of going through radium was simple. He had no idea what this was. This half-life of uranium is an enormous number, and there was no way to measure it. So obviously this would work, but with no knowledge of this value of the half-life for uranium, there was no way to actually make it work. In contrast, he could actually measure the decay of radium to essentially lead. The decay of radium. He could measure that in the laboratory, and so he actually could calculate what that value was. And so therefore, then using the intermediate, he could go back and making those complicated arguments I just described, actually derive essentially the same equation. He could sort of estimate then the value of this, the value of this stuff here based on his measured decay of radium and the assumption of equilibrium, and that of course, turned out to be 1 times 10 to the 10th, or 10 billion. So that's why he didn't go directly and consider the decay of uranium to lead, but had to consider the intermediary of radium, because that actually was decaying at a rate that he could actually measure.